thanks for inviting us. Glad to be here. So for today, I guess we're going to try to, what we do, we've been doing over the last couple of years, trying to build agents that do the work of humans, in particular human software engineers. And today, we're going to try to focus on showing, first of all, how does a system that kind of an agentic system that does the work of humans look like, what are the complications, and what are the steps in building such a system, right? And where we're even today, what are the limitations of the tools we have at our disposal today in building such a system? Because in our view, we're still at the beginning of how far maybe agents are going to go in doing the work of humans. We already talked about our backgrounds. I'm not going to go back to that. But you know, I think in many ways, I'm pretty sure, I mean, how many of you are using, let's say, LLM-based tools for coding? Yeah, like, actually, Gabor tells me he doesn't. He's like an artisanal. But you know, obviously, you know, coding, or I could say software engineering as we know it has changed, and we've seen it big time in coding, right? And you know, you've seen all the advances. Actually, GPT-5 dropped today. Let's see how that changes the world even further. But also, in our view, and for those of you maybe who have worked in the industry, you know, software engineering is not just coding. It's a lot more than that, right? And especially when you're trying to build something at scale, or when you're trying to run a large production system, code and, you know, feature development and, you know, solving hard problems in code is a big part of it. But it's also how does that all materialize in a production software system that, let's say, users access and, you know, use in performing whatever the task might be of that system. And in practice, the larger actually the system becomes, the more the complexity of the production, you know, or the complexity of the production increases more, and the more time it takes. And actually, the motivation for us in actually building agents for software engineering was exactly our own experience. In my last role, I was running a very large production system with a large engineering team. And over time, what we found is the vast majority of our time was spent in actually maintaining what we had and maybe like keeping it reliable rather than building new features. And also, no user ever complained because we delayed a feature. Many users complained when the system was unavailable. Now, let's go back to agents, or let's start with how, I guess, software engineers do their job today, right? Typically, you know, as software engineers, you're dealing with, you know, a plethora of different tools in different categories, right? There is tools around coding, there is tools in, you know, infrastructure, whether that's AWS services or Google Cloud, etc. There are usually observability and telemetry tools like Datadog, Splunk, etc. I guess by now, everybody's probably using coding tools. And, you know, there is then all the adjacencies around these things, right, that, you know, usually create like a software engineering kind of tool stack and environment. The majority of these tools require actually a human to interact like one-to-one, and oftentimes humans have to then take or give the input, take the output, and combine it with the outputs of other tools to perform a task oftentimes. And that's, humans are the glue. Maybe an improved version of this with agents is where we have agents, let's say, kind of performing its task or its category of tasks, and humans now are the glue across agents. And in many parts, we have moved to this you know, place today, right? Like take coding as an example, right? When we started using AI in coding, it was primarily auto-completion, or it was essentially trying to drive a little bit further the code generation. But by now, we've moved to actually asking an agent to perform a task, giving us the output, and us maybe incorporating that, right? But still, you might have an agent, let's say, that goes into like a production system. It maybe helps us with infrastructure, but humans are still the glue. Where we were headed, in my opinion, or maybe started touching, is now we have these multi-agent systems that take maybe an input from a human, they interact with other agents, they iterate, they plan, they reason, and they come back usually with an answer that oftentimes involves many, many tools and many categories of these tools, right? It might go from code to production telemetry to production infrastructure, interaction maybe with even other agents in other parts of the software stack. And I think today we're going to show you how you start essentially from the left of this, how you start with simple tools, maybe just simple LLMs, and you move towards building agents all the way to multi-agentic systems. Now, why this is a hard problem? It is because when you're dealing with all these different types of tools and different types of data, first of all, in each category, you have almost an infinite amount of possibilities in data. you have a lot of complexity that comes from dynamic environments, dynamic dependencies. You have on top of that a lot of what we call tribal or institutional knowledge that oftentimes exists in like large software systems, things that might be documented across multiple tools, or oftentimes are even undocumented, right? And people just know because they worked there for a while. So when you're trying to build agents, you have to take into consideration all of these things, right? The changing nature of the environment, the kind of code is self-documenting, but other types of data in an environment like this are not, the knowledge that is spread out across these tools, and a constantly changing world. But let me show you how maybe an agentic system for software engineering looks like. So I'm going to show you a very quick demo of how a system like Resolve looks like. First of all, think of it this as a multi-agent system, like I described, where you have agents that understand all the different types of tools that you find in a software engineering environment. You have infrastructure, and within infrastructure, you have a bunch of human tools, basically, that humans normally use to essentially perform tasks, like tools like Datadog or Kubernetes or Slack. You have tools that give you metrics, tools that give you events, code, GitHub in this case, et cetera, right? And each one of these categories, you might have multiple tools, right? So the point here is that when you're trying to perform a task, you might have to go across all of these tools. Let's start with actually kind of a simple task, or a simple problem, let's say, which is, let's say, maybe I'm a developer and some of my users are complaining about some problem, right? Let's say a bunch of users came and said like the UI has been slow this morning, let's say, right? How would I go about solving this? I would probably have to go figure out, are there dashboards, are there changes, are there feature flags that are on? Did somebody change the code in a way that maybe caused the problem? But let me ask actually now the agent this very high level question to see what it does. Let's see. So normally, like I said, in a scenario like this, when I have such a very high-level question, I would probably have to go across multiple tools, or maybe multiple agents, depending on how you want to see it. And I would start like looking at different things to see how can I figure out what's happening, right? So now what the agent does here, it actually takes this high-level directive, maps it to a set of tools, starts doing some planning even, right? Like to decide how to solve this problem. I understand my intention also, right? Like, and then it even maps it to part of the environment. I mentioned UI and maps this to the front end, which is a real service in this environment. And as you can see, it starts looking across all the tools that it has available to see if it can answer the question. Now, this is agentic in the sense that I ask a question at a very high level, that agent essentially decides, plans for itself, let's say, goes, executes a bunch of tools, and comes back. But still, it's not like a long-running agent, right? All it tries to do now is tries to answer my question the very specific way I asked it. While this is running, I'm going to kick this off, which is like a more kind of elaborate investigation where I ask an agent to go do all the work it needs to do in the background in answering the question, right? And I'm going to kick this off. Basically, I said like there is an API that is slow, and now as a background, like essentially, think of it as like an agent that runs for a very long kind of time, tries to do this long horizon task, where I say basically go and figure out what is happening and exhaust all the possibilities and then come back to me, right? So I'm going to let this run for a minute while I'm looking at this. Okay, so this came back, and basically it ran across all the tools that it has available and came back with some interesting charts to highlight and some answers, right? And it says basically that multiple spikes in the UI front-end latency were observed. It gives me like essentially a few different citations of what it found in different graphs, and says like the front-end experienced spikes in latency and a temporary flood of product lookup order processing errors during the time. This almost necessarily caused the degraded UI effectiveness. And I can ask now, can you go find the root cause? Which again, I'm giving it a very high-level directive. It will have to decide how to break this down to some sort of a plan, a bunch of tools to go execute, and come up with an answer, right? What a human engineer would do in a scenario like this. Okay, basically it came back and says, okay, I found the root cause at 8 a.m. This feature flag was intentionally enabled. I mean, sometimes it gets too smart. and by a scheduled cron job, and says that this was a chaos engineering. Basically, this was an induced failure, right? Like it understood that that's what it was, and tells me that this is what happened, right? And I can now say, how do I fix that? For example, right? And now complete the loop with me driving. Now, the other scenario I was showing you here is now where the agent essentially starts with a very high-level directive and tries to solve the problem by itself. So instead of a human now asking the question, the agent asks the question itself, right? So basically, it starts by asking 6 questions. And the directive I gave it was like there is an API that is slow, right? And now the agent asks the following 6 questions. What does the front-end service dashboard show around the alert? What causes high latency in this particular from traces? Were there any front-end service deployments or port restarts during this time, right? And each one of these questions, if I expand, basically you see that it's now the agent asking itself or asking the other agents, basically, for an answer, and even explaining what it asks, right? It says analyze the traces for request to this particular endpoint around this time. I need to identify which specific downstream service or call or internal function is the primary contributor to high latency. So imagine now this is like a human who's an expert in this, who received this high-level directive and is trying to solve it, right? And to do this, essentially it's going to go across all the tools, ask the right questions, get an answer back, right? So this gave some evidence, which now the agent takes into consideration and continues doing work. The other thing that you see here is that it used 3 memories, so it actually used some knowledge it already possessed about this environment, which goes back to the problem I was describing earlier. Okay, this gave me the fix. I can say give me the commands. Okay, this is how I turn off the feature flag, right? Like it's very straightforward. So I went from a high-level directive to working with the agent to give me the answers, right? And in this scenario, which is running in the background, you can see now that the agent is actually working with itself, with multiple agents, let's say, to get me to an answer, right? Which now you can think how to generalize even further, right? And any task that might require many, many steps. And let me show you how this looks in practice. Let's say now the agent that has all these capabilities can be on call like a human, right? So if I'm in this Slack channel, you can see that whenever an alert fires, this kind of software engineering or SRE agent basically can respond, acknowledge the alert, go use all the tools that it has available. The alert talks about like high latency some endpoint, and come back with an answer of what might be causing it, right? And it gives like an initial answer, which is like, here is what I observed in this environment. Here is my quick kind of set of evidence that I found. It seems like the evidence points to 2 downstream services, the recommendations and the ad service that might be causing high latency. It provides the evidence and then completes the investigation and comes back with a final answer where it says that the service high latency is the direct result of severe concurrent degradation into the downstream dependencies. The recommendation service spike to X amount of seconds due to an inefficient N+1 query problem in code. So it even points to the code as the problem, right? And I can say, okay, show me the code and give me a fix. Then now it kind of looks into the code, explains how the slow, essentially, what N+1 means, by the way, that you have a loop where every time the loop executes, you run a database query, so the latency accumulates, right? And it gave me an example of how to fix this in code, and I guess this is still running. But I'll stop the demo here, right? But the idea here is that now the agent that is executing on its own is going to run basically multiple iterations. In each iteration, it's going to ask a bunch of questions, it's going to perform some tasks, and come back with some answers until it completes the task all the way to the end. And with that, I hope this gave you a good idea of what is the goal here, what the agents were trying to build doing, and maybe go to how we're actually building them. Bharat, you know? Oh, sorry.
Could you speak to how much of the decision tree was automatically figured out versus how much of the decision tree was coded?
It's all automatic, right? And I guess that's a good question, right? So the question is basically, okay, given a high-level directive, right, how much of the decisions the agents have to make are hard-coded versus, completely free-form? I mean, the goal is for it to be completely free-form. Now, the reality of the situation today with models is that if you just give tools, the tools to the models, they're probably going to go off the rails very quickly. So it's not hard-coded for sure, but let's say the planning phase, we do a lot of hand-holding. The models design the plan, but essentially we constrain quite a bit what the plan can look like. in the end result, or in the final state, ideally you want the model to completely plan on its own, iterate on its own, decide what to do, right? For now, I guess a lot of the planning and reasoning part at that level is controlled, but it's not hard-coded, right? It's mostly, you ask for a plan that is very, very constrained, right? That kind of you have guardrails around.
One more follow-up. So if you have a working system and you add a new feature, would you suggest that the new feature would also need handholding for the first few, let's say, cycles, and then the system will adapt?
New feature in
iterative development, I built and launched the system. 3 weeks later, I add a feature, and now for the new feature, do I need new capability to handhold the system while it runs?
No, you don't, right? And I guess if you truly are trying to build, in my opinion, an agent that can maybe do the work of humans, it has to learn like a human almost, right? And to learn like a human in that scenario, you probably has to look into code that you created and understand what the code does basically, right? Or if you added new telemetry or something else, it needs to look into that and kind of maybe learn from it, right? If you have to every time teach the system, that doesn't scale. I mean, you want to be able to teach the system, but not for every particular thing you do, right? But maybe for higher level patterns. I was hoping this is going to finish and you will see the end result, but I guess maybe let me show it from here, what it looks like. So the end state of this is when the agent completed its question and answering sequence, it did a lot of work, it iterated until it got to a satisfactory answer for itself and gave me an answer of what the problem might be, right, and how to solve it. And with that, I'll give it to Bharat to continue. I mean, I guess that's the flow I was showing, basically.
So now I know that was like a pretty good demo, right? And we are all thinking, how do we build such a multi-agent system by ourselves? But before we do that, I want to introduce you to the foundational principle of building a multi-agent system. Keep it simple. Because not every problem really requires a multi-agent system. Some problems can do with very simple solutions. And if it is possible like that, then we should definitely do that. So what we are going to do is discover what is the right level of agentic complexity for a particular task and how complex should our system be. And to do this, we will start from building from a simple LLM call all the way to a multi-agent system. On the way, we'll add feedback loops, tool use, make it into an agentic system, and then add multi-agents. And at each level, we'll try to answer 2 questions. What kinds of problems can this system solve? And more importantly, what kinds can it not? We'll have a running example of a payment system failure. It's a great use case. Sometimes the failure reason is obvious. Sometimes it's a tangled mess that spans multiple systems. This progression will show you exactly when each level becomes necessary. And by the end of this talk, you won't just know how to build agents. You'll know how to build the right agent for your problem. Because in production, the simplest solution that works is usually the best solution. So with that, let's start simple. So here, the most basic setup is a single pass LLM call. One prompt goes in, one response comes out. That's it. And for a surprisingly high number of use cases, this actually works. If you give the LLM the right inputs, the right prompt, transform the inputs properly, and interpret the output correctly, then this is enough a lot of the times. Let's look at one specific example for this. So in this task, what you see is, okay, the situation is the payment system is on fire. Users are flooding support. Your phone is blowing up at 2 a.m. And in a panic, you open PagerDuty, look at the incidents and tickets assigned to you. You check the dashboards and try to figure out what metrics are going off the rails. And you check for the underlying dependencies, look at what was pushed to production recently, and start targeted log queries with some hunches on what you think the problem is. And iteratively refine the queries to get to the stage where you have, like, let's say 1,000 log lines. And then you plug this into any LLM that you like and ask it, why are these payments failing? And the LLM scans the logs and it figures out that there's one specific log that says card expired and says, looks like the card expired and that's the issue. But if that's right, fantastic, problem solved. But what if the error that it pointed to is just noise? What if 80% of the payments are actually timing out because of a network issue that's in some other log that you never posted? The LLM didn't know enough to ask the right questions. It didn't verify its hypothesis. It didn't try to reconcile the answer against all the failures. It just spotted a pattern, answered the exact question asked, and quit. So these are the exact limitations of a single pass LLM system. It has no internal feedback loop, no way to evaluate or refine its own response. There's no iterative reasoning, no mechanism to course correct once you go off the rails, and no concept of uncertainty. So there's no way to know if it's actually confident in what it said or not. It's like asking someone a hard question and blindly trusting their first instinct. This might work for simple tasks, but as complexity rises, the cracks start to show and the system breaks down. So we move on to the next step, the actor-critic system. What are we missing? A feedback loop, right? So we add a critic LLM here that is supposed to give us feedback every time we propose a candidate solution. So the flow goes like this. The actor proposes a candidate solution based on prior inputs and feedback. The critic LLM examines the candidate and it has its own prompt and it also has access to the input, and it says whether it looks like this is the right solution to this. And if it makes sense, if the critic approves, we return this candidate as the solution. If not, we go back to the actor with this feedback and ask, okay, based on this feedback, do you have any other things that you want to try out? And this keeps on repeating. So let's go to our example here. The actor now says card payments are failing because the card is expired, just like before. The critic responds, that's the only log message that I see is troublesome, but card expirations are usually one-off. They wouldn't explain widespread failures. So the actor adjusts its response to the user that, okay, what I see is a card expiration failure, but I don't think that's the issue. So maybe there's something else that you should look at. And that is already much better than the initial response we got. So, but then what are the limitations of this system? It can't do a few things. It's still limited to what the user pasted in the first few log lines. It can't query new data or explore beyond what's given in its context. Second, there's no persistent memory. If the actor and critic keep going at it, let's say 10, 20, 100 times, they might still forget what happened in iteration 1 and then be stuck in a continuous loop. Third, it's still bound by fundamental limitations of LLMs, like context window limitations, lack of math skills, not being able to count the number of R's in strawberry, and hallucinations. Finally, there's no access to external knowledge. It can't Google, it can't look at the latest Stack Exchange article for this specific answer. So that brings us to a good point where we define tools. What is a tool? A tool is any external function that the LLM can use to interact with the environment. This might mean querying a database, calling a calculator, or asking a follow-up question to the user themselves. Tools solve many problems. They enable environment interaction, memory, math capabilities, and access to external knowledge. So now that was what LLM means to us. What does a LLM look like? What does a tool look like to an LLM? So to an LLM, tools are defined in the prompt as structured interfaces. Each tool has a name, which is an identifier, a description, and which is what does it do, what does that tool do, what does it doesn't do, what does it need, an input schema, which are the parameters defined by the type and what values they take, and a usage and all of this can be called like a usage protocol for the LLM tooling. Now, when the LLM wants to use a tool, it emits a structured output call. The format of the call can depend on what LLM it is, but it essentially looks maybe like a JSON. The execution engine then runs this tool and returns the result to the LLM, which then decides what to do with the results. So this is what a LLM with tool use looks like. There's some pseudocode here, but what's essentially happening is at each step, the LLM sees the current state, the tools available to it, the input, the previous tool call results, and its own prompt. It generates a new candidate, possibly with tool calls. The execution engine executes these tool calls and appends the results. Then the LLM evaluates, did I solve the problem yet? If not, it loops again. If yes, it returns that answer. By the way, I forgot to tell, if you want to ask questions, you can obviously ask anytime. We'll also have a question answer session at the end. So let's go back to our example. Now, the user just says, this time look carefully. The user doesn't paste the logs. It just says, it checked the dashboard and it said the payments keep failing. Check the logs. Now, the LLM itself decided which logs to check, how to formulate a log query. That's also not regular things that we write, right? That's a specific syntax. The LLM figured it out. It sent that query as a tool call to our Loki agent, to the Loki system, which then returned the logs. Then the LLM analyzed those logs, figured out what the issue was, and posted it. So this time it was able to get to a different state because it had access to tool calling. So it figured out, okay, that's maybe not the log to look at. I need to look at some other logs, and it kept iterating over that. So it found out that there's some network issues around Stripe availability. And now, so this looks good, but what are the limitations with tool use? Even with tool use, LLMs have some limitations. There's no state tracking. They struggle to manage evolving task states. Tool failures are one other thing. While some of that can be handled in the prompt, still LLMs may not be able to handle every possible error in the tools. There's no real planning happening here. The LLMs are more reactive. Okay, I have to solve this problem. What are the tools? I do that. I got the result. What do I do? There's no real planning on the overarching task objective. And there's a lot of inefficiency around poorly used tool calls, calling tools that you don't really need, maybe because you just want to be comprehensive. So things like that. So based on that, let's go to agents. So what is an agent? Isn't it LLM with a tool call an agent? It is if there is a couple of things that are figured out. If we add a planning loop where the LLM can reason about a task, break it into steps, and act as its own feedback agent. Second, if there's an autonomous execution engine as well, if the LLM can autonomously execute on long-running tasks. To support that, agents usually have memories, reflection, and internal sub-goals. Instead of just reacting, they now have a plan which they enact out strategically. And this is what an LLM agent looks like. It comes in with a directive, it reasons about the directive, then it does some tool calls, which can be called the action, then it observes what the result is, it replans around it, reasons around what the outcomes were, and keeps doing this until it has a result, which is then helping it achieve its goal. So this is what an AI agent looks like. As you see on the right, there's reasoning capabilities added, tools as usual, an execution loop, memory, and guardrails. Guardrails, as Spiros was mentioning earlier, they are things to constrain the output space of the LLM. Otherwise, LLMs today are not good enough where they can do everything by themselves, or they don't know things not to venture in. For example, let's say it starts writing some code to fix the issue when we had just asked for logs. So you want to have those guardrails around. So that's usually a part of agents today. Sorry, yeah.
So you mentioned that reasoning is a different part of the environment than execution. When you say like the reasoning capabilities are added to the agent, so like how are these capabilities added? Is it like you chain multiple prompts together, or is the reasoning within the loop itself, or is it something else?
So usually there's multiple ways to do it. There's no right or wrong answer here. Some of the ways that is done is, one is that the agent prompt itself has a reasoning criteria or a reasoning stage. So every time it gets some new information, it reasons what to do with it and then has some next steps. Maybe it's a list of steps already in the prompt. Maybe it is something it decides dynamically and then does that. Sometimes it is externally enforced, where an external agent is basically prompting it with a different prompt each time, saying, okay, now it's time to reason. Now it's time to act. Now it's time to do this. Both are agents, essentially. One is more autonomous. One is more structured or hand-holded in some sense. But yeah.
So it could be like both like predefined reasoning steps, or like maybe just like telling it after this, do lots of reasoning, like telling lots of specific things.
Yes, a lot of the times how that is done, like when you have it autonomously happening, it's done usually in the post-training or RL phase where they are taught to be doing these things. When they are taught to follow user inputs, they're taught to go about this loop. So it's usually handled at that stage where it is able to do certain things autonomously. Even then, not everything is possible, which is why we usually have some structure outside the LLM to support it. Yes, so Yeah, so I think we covered this, how this is happening. At every stage, it starts with a system prompt and memory, generates a sub-goal or a plan, calls tools, reflects on the results, updates the memory with the outcomes of the tools, checks if the directive got complete, loops until satisfied, return the solution. Okay, so let's go back to our problem. Now what's happening? Now the LLM has access to even more tools. It has access to a dashboard tool, it has access to a logs tool, and what it is going to do, the user just told us what it got in PagerDuty. Payments keep failing. Now the agent checks the dashboards to find out which service is failing, and note that this is an iterative process in itself. It might not find the right dashboard in its first try. It might go look at some dashboard, find, oh, nothing there, or some hint of something there, and go to another dashboard. Once it finds the right dashboard, it knows what service logs to look at, and then it queries the service tool call. The agent then queries the log, gets nothing, reflects, adjusts its query parameters, and gets something out. And we are again back to, there's a network error connecting to Stripe which may be causing your payments to fail. But for all the benefits that agents offer us, they do have some practical limitations. First, there's the breadth versus depth dilemma. One agent can't be an expert in everything. Our hope is that LLMs can be jacks of all trades. But today, the reality is that they're master of none. So it's more, so a lot of the times, one LLM can't be expected to do everything possible that you need to do. For example, to solve a complex enough task. Then there's the planning fragility. LLMs can very easily lose track of their main goals as they get sidetracked in subtasks. For example, let's say the previous LLM got stuck in creating that log query. For some reason, it was never getting the logs. It would keep looping there, and trying to fix that. Or maybe it saw some error and it saw some error loop and it got stuck there. It forgot what the user really cared about. So that is something that is a problem with single agent systems. Then there's a centralized bottleneck problem. Every decision flows through this main LLM, making the entire process bottlenecked by how fast your API provider is. And then there's the error propagation. Murphy's law still applies. Anything that can go wrong will go wrong, and one bad guess can derail the entire conversation flow. Then there's the problem of tool overload. To solve a good enough complex task, you need hundreds of tools. They can be as simple as checking the time to as complex as fetching those logs. And if one agent is supposed to do everything, then it needs access to all these tools, and managing access to hundreds of tools can be overwhelming. So what's next? Just like real-world teams have specialists, that's why any agentic systems that are solving complex real-world problems need multiple agents. And to talk more about this, I'm passing it on to my colleague Gabor.
One question before you go. In the LLM feedback method, we had an actor critic.
Yes.
Do we no longer have a critic in the agent universe to catch some of the error propagation?
Yes, so we do, but it depends. Since we're talking about a single agent system, it's built into the LLM. So when we are talking about the execution loop, the reasoning loop, it acts as a critic for its current hypothesis as well, before deciding whether to go for more tool calls, output the answer, or...
You're saying even with that critic, error propagation does happen?
Yeah, there's multiple reasons, like LLMs are not perfect. So yeah, it does happen. 1 second, sorry, yeah.
I have a question about the tool call. How do you constrain the tool call not to do like destructive things? For example, if you have a tool call from terminal, how do you know it's not deleting things, but sometimes maybe the answer is to delete things?
Okay, so very good question. So here the thing is.
Oh, you want to do the question? Could you repeat the question for the online?
Oh, my bad. Sorry. So the question is, and correct me if I'm wrong, how do you constrain the tool call to do things, to only do things which are which don't destroy systems, or like let's say rm minus rf slash, and if you do that, then how do you do things that you really want to do? Maybe delete a file. So the answer to that is it's up to you. So you can define a rm command that doesn't. So you can define a tool call that will never call rm, and you are doing that through code. So your terminal that you are giving the LLM access to, it doesn't have the possibility of calling an rm, because you have an if statement at the end in that program of the terminal that never do RM, do the rest of the things. And so the LLM never has access to it. And you can also prompt it saying that you can never delete, but it won't respect that. You shouldn't trust that it will respect that, but that's handled at the end of the tool. As for your second question, like, okay, but now that we have restricted RM, how do we do RM if we need? So we have to provide that as an API, and we have to make sure that it doesn't do destructive things at the tool call end. We can't trust the LLMs today. So yeah, if you're going to build that system, then constrain it to things that you are confident about. Yeah.
It's a pretty fascinating system and train architecture. So I guess two questions kind of go side by side. First one is, I mean, how do you go about doing, like, evaluate and verify the results, right? Because this is a fairly complicated system. Most benchmarks are there aren't really about, doing operations. It's mostly about solving like puzzles, right? So this, I guess, that's kind of my question number one. And my question number two here is, let's say evaluate it. How do you go about debugging this system? There's so many moving pieces here.
Very nice question, and that is exactly why. So two questions here. The first question was, given that this is a decently complex system, how do you build evaluations for it? Because no existing evaluation frameworks or test sets out there really match the system. And the second question was, now that you have built the evaluation, how do you go about debugging it if it's failing? And the answer to the first question is, you build two types of evaluations. You build evaluations for every step of the pipeline. And for gathering data for that evaluation, you do all kinds of hacks. So for example, let's say I have to build an evaluation for how good my log queries are. How will I do that? I can just give a different LLM a prompt that generate log queries. I don't care what they are. Just generate log queries. I'll validate them against a running database and make sure that the log queries return results. So whatever succeeded there, I'll use that as a training data for my LLM. And sometimes it can be done in a fashion where not even training data, even as prompt injection, like few short examples for my LLM, and sometimes even for training. The other way to do it is if use a bigger LLM to generate those queries, or a specialized LLM that's trained on that data to do that for your regular LLM that you're using in your application. Why not use the bigger LLM? Because it's costlier to use, it's an overkill, it has a higher latency, things like that. But yeah, it's an evolving field. There's no clear answers. And one of the most important parts with building a big system is gathering the right data. So there's two kinds of data together, one for every small part you're doing and one for the overall end-to-end task. Even if you build a good system for every small task, you might be failing on the big task. And how do you go debugging that? You basically look at what the LLM was doing. You either manually verify it. If it's a really hard task or it's really long to look at, you send it to a different LLM which has maybe a different bias who tries to debug it or categorize it into certain issues that then you can think about how to incorporate into your prompts or your training procedure. Does that answer your question?
Yes.
Yeah. Okay, so with that, I'll pass on to Gabor, who will talk about multi-agent systems.
Thank you. So I guess I get the last section, the grand finale, so to speak. When we put everything together and get sort of a multi-agent, more distributed sort of agentive system, throughout this part, I'm going to lean hard into the analogy of these sorts of systems as similar to the complexity that we see in large coding systems. So if you imagine an agent as a function, then like a multi-agent system is a program. If you imagine an agent as a service, a multi-agent system is a distributed system. And going maybe back to the very beginning, the advice I always got for building a distributed system is step one, don't. And step two, okay, let's think through it carefully and what the complexities are. So we'll get to that in a bit. But first, what do we get? Like, why should we do this? The main reason is we address a lot of the limitations that a single agent system can see. So a lot of these fall into a similar category of encapsulation, where for specialization, in a single agent system handling, let's say, logs and dashboards, the same agent has to know a lot about logs and know a lot about dashboards in sort of the same prompt. If you break it up into two agents, you can have one that's just specialized on logs, one that's just specialized on dashboards, one that's maybe just specialized on code and whatever else you need to do. Similarly, sort of long-running tasks and long context tasks, instead of having a single thread where you sort of iterate on the right log query maybe and search across dashboards, or like you've all presumably seen Claude go search a whole bunch of stuff in code. Eventually, when you start composing this, then you blow out your context window, and most of that context isn't even particularly relevant for like the next step that you want to take. Centralized decisions, similar theme. Rather than having one agent that has to make the next decision across 100 different tools that you call, you can split this up so that each of the sub-agents sees maybe 10 tools, and then there's an orchestrator that sees the 10 sub-agents that it can orchestrate between. Errors, in a similar vein, someone had a question about, like, do you still see these sorts of errors when the agent is self-critiquing itself, has its own critique loop? And multi-agent systems can add another level of protection on this, where in part just the distribution of these tasks means that there's more critiquing steps before it gets to the user. In part, like, you can even pull out the critiquing model, similar to actually how it was in the very beginning, as a separate agent that goes back and forth. And then tool context overload. So similarly, if you have too many tools, then breaking up into agents can help. The short of this is you can think of it as you break up these systems into multi-agent systems for the same reason you break up code into multi-service or multi-function code. If a single function gets too long, if it's doing too much, if it's too hard to debug, it's very useful to break it up and get sort of higher performance that way. And we can look at what this looks like. So going back to our classic example, payments keep failing. And you can even see this kind of looks almost like a code trace. You can have the message come into the orchestrator agent, and maybe it'll call out to logs and dashboards simultaneously. And here it doesn't have to construct the log query. It doesn't have to construct like the dashboard metric query or search for the right dashboard. It just says like, hey logs, find logs related to payments failing. And then the logs task goes off and does its own thing and comes back and says like, hey, it looks like maybe Stripe is failing due to timeouts here. Dashboards maybe comes back and says, hey, it's probably the checkout service that's broken. And then the main orchestrator agent in this paradigm can take those two together, can say, aha, okay, I think I understand what's going on here. Clearly, checkout service is failing on Stripe timeouts. That seems like a reasonable thing that would cause me to be paged at 2 in the morning. Maybe let's go off to the code agent and be like, code agent, please go fix it. Increase the Stripe timeout in the checkout service. And it goes off. And at some point it gets long to show all the things the system is doing, but eventually you come back with a full remediation of the problem. And the elegance here, there's a lot more on the right-hand side. There's a lot more that you as the developer have to build, you as the AI engineer have to build, but the interface is much nicer. Hey, I have a problem, go fix it. And then a multi-agent system can do all the things it needs to do to be like, here's your solution, congratulations. All right, so how do we build them? Again, leaning into the analogy, you can do whatever you want to a first approximation, but there are patterns that at least people have traditionally used in industry. This is not an exhaustive list, but maybe a sampling. Scatter gather is a common simple version, sort of the MapReduce equivalent. You have an agent that kicks off a bunch of subtasks, collects the results, and then summarizes it to the user. So if we go to the observability example, maybe even a deterministic agent, quote unquote, that goes off and says, call all of the systems that I have access to, all the dashboards, all the logs, just get all the evidence that I have. All of these sub-agents figure out whatever they need to figure out. They come back, and then maybe there's an agent that summarizes and says, well, based off the evidence, this is what I think might be wrong in the scatter-gather framework. Orchestrator loops is effectively what I showed here. This is my personal favorite, or I guess native way to build agents, where you have an orchestrator that figures out some subset of agents to call, goes off, calls them, gets the result back, decides, okay, based off this, I think I'm not done yet, I need to call these agents, goes off, calls them, gets the result back. You can think of it as like chained scatter-gather. In the degenerate case, always calling one agent. In sort of the fancier case, you can call multiple in parallel. And on the other extreme, you can have just free-for-all. Agents are calling each other willy-nilly here and there. For folks here that like the actor model of programming, this is a similar mindset in many senses. Like there's a shared context, and the agents just like hand off to each other is the common way this happens. All right, so what are the interesting implications of these different designs? One that at least I think a lot about, and so you guys are going to have to hear about, is multi-agent context. So for each of these agents, you have to decide what goes into the system prompt, what fraction of the conversation, and the internal agent trace you show them. So in this case, like you have an orchestrator, it calls 2 agents. Agent P calls 2 agents. What does subagent B2, the bottom right here, see of this whole trace that happened? Where like one extreme, you see everything. It's just the whole conversation trace and like internal trace across these agents. The advantage here, you see everything. So like you're not going to like lose information or have something lost in translation anywhere. The disadvantage, you see everything. So like you're going to blow out your context. You have many of the same concerns of like why is the code agent, let's say subagent P2, here caring about the particular output from like the dashboard agent in its full glory. So this, in my view, this sort of global scope works actually really well for like the free-for-all types of agents. It's probably less necessary and less useful for scatter-gather, orchestrator, loop type architectures. On the other extreme, you can have, all you see is your own input. So going back to the programming analogy, each agent is like an RPC. It sees the request that it gets in, but it has no idea where the request came from or what else is happening in the system. It's just, here's a request, I need to fulfill it. Wonderful for debuggability. You can, hill climb on how the subagent works in isolation from the whole system. Wonderful for sort of the simplicity of understanding what's going on in the system. But you have to make sure the request has everything the agent needs to do a good job. So if subagent B1 did something that it either forgot to pass up or agent B forgot to pass in, or if there's like some large artifact that you're modifying that you don't necessarily want to pass all the way through the whole chain, then this starts to encounter limitations. And there's any number of in-betweens here. My favorite being sort of a call stack approach. An agent sees where it came from. It sees all the calls that went into calling that agent, but not necessarily all the other stuff that happened elsewhere in the system. So like there's a bound in the tree depth of what it sees, but it still gets some more context than it might otherwise. Related question, what is the statefulness of these agents? And here, like you can think of it as 2 different analogies. In one extreme, they're fully stateful. They behave kind of like humans, where if like I go and talk to Spiros and I ask him a question and then I ask a follow-up, Spiros knows my first question. So the follow-up is sensical. He can take that context and continue answering. In the other case, these agents behave much more like RPCs or functions, where if you make a request and then you make another request, the other request doesn't know the last request that came in. Why would it? Same sort of trade-offs here, where like actually in my personal view, for more like free-for-all-ish agents, actor models of agents, it's even in the name actors, it makes more sense to have this more stateful agent for orchestrator and worker type workflows. I at least tend to like the more stateless agent, or more limited state at least, between calls. And all this becomes a lot more complicated when you start thinking about async activities. Which is super important from like a UX point of view. Generally speaking, you don't want all of these agents to happen one after another, because then it'll take forever. Generally speaking, you want to propagate to what's happening, what agents are being called. You saw in the demo fairly quickly after you said the question, it'll show like looking for dashboards, looking for logs in parallel, and kind of showed progress updates of I'm looking at this in particular and that in particular. But now, what do you pass in for context? Like if you do want to pass, for example, more global context, but some tasks are still standing, what do you do there? If you have a stateful agent, but you're invoking it 2 times in parallel, what do you do there? I don't have answers on this slide. The best I can do is, the same sorts of considerations you have for any large distributed parallel system. They map, in my mind, pretty well to the multi-agent architecture world. All right, that's the end for architecture. Do I have questions? Questions, excellent.
Yes. Again, I think it's really interesting that you mentioned the after programming model. It sounds like what's missing is kind of like a goal layer for agents, right? I mean, you have the actors and you have the task list layer to foster for workers. So I was wondering if you guys are thinking, let's say, like building out kind of like this distributed programming network just for agent execution.
So
you have to kind of like write everything by hand.
So the question was whether there are distributed programming languages for agent execution or whether we have to write everything by hand?
Yes.
I mean, there certainly are. There's probably hundreds of startups writing agent orchestration frameworks, LangChain, LangGraph being the most famous of them. So you don't have to write all of this by hand. You can do something more straightforward. You mentioned actors in particular as a model. So for their keeping track of the goal, the easiest solution is you just track the whole conversation. So a user message comes in, and then the agent one decides, hey, here's my initial response to the user conversation into like almost a scratch pad. Agent 2 sees the conversation, including agent 1's reply, and sort of it keeps going that way until they decide that they're ready to respond to the user. Did that answer the question?
Yes.
Excellent.
I have a question about context and memory. So over here you mentioned like context is like what does each agent need to get as input. I think it's like the prompt, but then what's the difference between that and what you just mentioned before?
Good question. So we'll get into that some coming soon. But the short answer is context is indeed the prompt. So it's usually the system instructions, the conversation context so far is the most expensive part. Memory is additional information that you're pulling in to help this agent do well based off of past experiences. The core problem here being agents are fundamental, like LLMs, I should say, are fundamentally stateless. You get the same request and you set the temperature to 0 and you'll get approximately the same result.
What goes into the process of making the agent specialize the task beyond fine-tuning?
Yeah, it can be any number of... Oh, sorry, the question, yes. The question was what goes into making an agent specialized beyond, say, fine-tuning the LLM. And fine-tuning is one of the things you can do. So you can have particular agents that have their own data sets, their own tasks. You give them data, and then sort of they do their own thing. Prompting is the other. So either wholesale replacing the system prompt, or occasionally there's like a shared part of the system prompt, and then you replace particular instructions. Like you're a researcher, here's how you reply, here's how you call tools. But like you're a particular researcher for logs or for dashboards. I'll go back there because I think you had your hand up first. Yes.
All right. So I was wondering, are we not going to have perpetually runnable agents unless we solve this context window problem without like ad hoc solutions like that?
So the question was, can we have perpetually running agents without solving the context window problem? The short answer is yes. You'll eventually exhaust your context window. There are a couple things you can do to mitigate this. One is you can periodically summarize your context window, and then you actually can have just one agent that keeps going, albeit now you have a lossy context. The other, well, okay, multi-agents help some in that you don't have to care about the context window growth from the sub-agents that you call, or your sibling agents. But even there, like the orchestrator can't go forever, or else eventually it's going to run out of context.
So from the beginning, I haven't seen how disrupted the reliability systems in general in production. So let's say someone has to use async for their own in-house production software or something. Can they get to choose the LLM they want to use from their overall production software, or is something comes with inbuilt LLM? Like let's say if you use Cursor, you get to choose Claude or GPT or whatever it is. But here we're using LLMs to the in-house, or is something you can choose to be able to use.
Gabor, do you want to answer this? Because I think this is not so much like what we do ourselves, right? But I think an interesting observation to your point is I think the question was like, in a system like this, can you choose your own model? Or, you know, does the system come with models? I think actually in some sense, like maybe this is a next evolution of how these things work, right? Because you can think of, let's say, agents that are simply the orchestration of top of any model, and there's more like a single agent paradigm. And let's say coding agents is a good example of that, because for the most part they use one model to do all the work, because they're also dealing with one modality of data. In a system like this, I mean, in theory, yes, you could, but in practice, you know, what we found ourselves at least is that different models behave better for different tasks, right? And I think you want to have this ability of routing and choosing the right model, either for latency, reasoning, cost even, right? If the same task can be performed equally well for a very cheap model and a much more expensive inference-wise model, you want to use probably the best model. So yeah, in theory, nothing prevents you from plugging in your own models. In practice, I think when you move to this multi-agent system, most likely this is essentially you have a big gap between the model and the end task. So I don't think it makes much sense. Feel free to add, by the way.
No, I tend to agree. Like I think these make the most sense when the cost is passed through. So like you, the user, can choose to like do cursor cheaper, more expensive, or what have you. And in this case, it's more like we just need the task to work well, and we've tuned these models pretty carefully.
And I also think the world is moving more towards this model as well than the user picking their model, even in coding itself, I think.
I'm currently working on a project, multi-agent project using Creo AI. I just had a question. Like, I saw a few issues when I was working. One was the issue that Creo AI was launched in 2023. That was in GPT-3 era, and at that time, I realized that he had a very smaller context window in his memories in LLM. Now, like today ChatGPT-5 was released, and we have like 400,000 tokens that it can take. So we need like lesser and lesser amount of LLMs required in multi-agent system. So I feel like with better agents in the future, maybe because we have larger memories in one LLM, we might decrease. We might just get rid of multi-agent systems. Do you think that's a possibility?
There is definitely some of this. So like the adage remains that if you can get away without a multi-agent system, you probably should. For context windows in particular, the very long context windows aren't free. So they're all doing some amount of summarization, basically, of the context. Like attention itself is quadratic. You're not going to get truly a 400,000 or 1 million by 1 million runtime out of these systems. And so empirically what happens is when you grow past the like true context window, the performance starts to steadily degrade, which is sometimes okay and sometimes not.
Do you see them going like long term or like time over? That's
and I forgot to repeat the question. The question was about long context windows and whether those will make multi-agent systems obsolete. The question was, do you think this will degrade over time?
What's the end game?
What's the end game here?
Of context.
I mean, I should probably not be in the business of predicting things with AI nowadays. My own philosophy is these LLMs will continue to get smarter. Nowadays, fairly predictably. Over the last couple of years, it's been like there haven't been as many nonlinearities as there were in the early days. And there will always be more that we want to do with them. And so things that used to need multi-agent systems will migrate to being doable with a single LLM, and then there will be new things that now we want to do on top of them that will need their own multi-agent systems of these larger primitives.
So I was wondering for a problem, especially as hard as like software engineering, probably very expensive in terms of tokens. I just wanted to know like what are the strategies you can use to be more token efficient?
What are strategies you can use to be more token efficient?
I'll give you an answer, which is that software engineering is also very expensive.
It's a good answer.
No, like jokes aside, the good thing about like when you're solving hard problems is that humans take a lot of time to solve them too, and so tokens are less of an issue. If you're solving simple problems, then actually tokens matter a lot more. In a way, I almost see that when we use more tokens in performing a task, I almost see it as a good thing. Not like in a wasteful sense, but in the sense that, okay, if a human had to perform the equivalent amount of work, it would take them a long time and it costs a lot more, let's say, in terms of effort. And of course, more so when you're dealing with like stressful tasks, right? Like, okay, something is wrong and I need to fix it right now. But I don't know if you want to talk about strategies in conserving tokens.
I think that's the best answer. That make sure the tokens that you're using are for a cause that it's worth the tokens. The other thing that I can point out is you can memoize, in a sense, past results. It's like a common strategy here is you output to some sort of scratchpad or file system or what have you, and then you don't have to recompute things over and over again. You can make use of this partial computation to hopefully make things more efficient.
You have the question?
Yes.
I have a mic, so I'll save you the trouble of repeating. I found it fascinating that a lot of what you said, all of you said, is mapping a lot of what's going on and explaining it with, say, distributed computing or good software engineering principles, which makes me very happy because then what we teach in class or what we learn, hopefully those principles remain. You mentioned MapReduce, you mentioned global context, local context, big program, splitting things into smaller functions. So I'm curious personally, is there any place where you've seen this paradigm starting to break down as perhaps those things don't map as nicely?
Evals. And this gets back to the question a while ago of how do you evaluate these systems? And to some degree it maps. To some degree you have individual prompts, and I think you covered this, that you can test and make sure that on some fixed test set you get some amount of accuracy. But taking the analogy, all your tests are flaky by nature. You're looking at a number rather than looking at, it passed all the unit tests, fine, I can deploy. And then end to end, especially when you get into these multi-agent systems, it becomes much harder to figure out. Oftentimes the task is complex enough it's hard to figure out, did you do a good job or not? Did you do a better job than this other system that's also behaving stochastically? And even if you do have that, how do you attribute what went better or what went worse to the right origin? It's this is where you get into RL-ish exercises of how do you do credit attribution? How do you sort of propagate a reward back into the system in meaningful ways? I don't know, did that answer the question?
It did, and I'm glad you mentioned RL. We've just covered that in the class, so if you have any context on that, if it's coming later or now, that would be great to mention as well. Everybody knows RL here.
It's that's the way to do it. I don't think the talk actually has much about RL, but we can answer some questions about it. All right, maybe, okay, one more question and then I'll go through the rest of the slides.
RL question. So let's say you run this at 2 a.m. today, and tomorrow at 2 a.m. happens again. Does your system have the ability to learn, last time I did the same thing, I did it this way, and save some compute costs?
That is an excellent question. The question was, if you get an alert, yesterday at 2 a.m. and now and you fixed it, and now you get it again today, can you remember what you did yesterday to do a better job today? Which is exactly what we're talking about next. So, exactly, these multi-agent systems do want to learn. One of the main weaknesses of LLMs is that they're inherently purely functional. You pass in the same input and you get the same output, which is terrible if you just taught the system that no, this particular alert in this example is because the customer service is down. See this dashboard to check what the error rate there is. And then the next day you get the same alert. And in this case, resolve gives you the same issue of hey, I got a log indicating that this not actually the root cause is the issue. So how do we learn? How do we not make the same mistake over and over again? I'll at least highlight two standard strategies. One is post-training. So, post-training, adding new training data, and then retraining the model, and now it gets smarter. This is sort of the classic ML approach. If the model messes up on something, add a data point, it gets better. Or learning through memory. There was a question a bit ago about context versus memory. So memory here is for exactly this sort of learning, where you keep basically an external scratchpad, an external database of the things that you remember, the things that you already know to be true about the system. And then you pull bits of it into whatever prompt you're running at the time, whatever agent you're running at the time as relevant. So sort of I'll lean into the software analogy, either updating the code to make it natively know about this thing that you want, or like writing your configs, writing your memory to a database, and then pulling that information on the fly. Going like one level more in detail, like here we have our same example. I'm getting an alert. I found a log indicating that we're timing out, and then the user says like, no, the actual issue isn't the timeout. It's that like the customer service is down. You should be paging them instead. Here you might add a data point that says like, hey, when you get the input, I'm getting an alert about blah, blah, blah. What you should be doing is you should be calling this tool or should be calling this agent. And then now, the next time when it sees this input or something similar, it'll say, aha, it's like just natively baked into my weights that this string maps to this tool that I should call in the future. Other approach, you add a memory here that says, hey, let's say when query, then do this. And then the next time we run it, we pull this into the context of the model. So we have like the system instructions, the conversation so far, and like a set of relevant things that we have to remember and keep in mind. And then the hope is that the model's native instruction following will pick up on this and say, hey, I recognize that I have instructions in my context that say like when this happens, do this instead. Both of these have pros and cons. The pro of training is you generally get higher consistency because you baked it into the weights. You don't have to rely on the model being good at like this abstract instruction following. And related to that, you can teach it whatever you want. Like you can get the model to do some weird stuff if you bake it into the weights. The downside, you have to retrain a model, which is expensive, both in terms of human time to get it right, to get all the evals in order, and expensive in terms of like GPU time, like literal money cost. It's harder to translate from model to model, and it's especially hard to get post-training of any sort, like SFT especially, but RL as well to some degree, to maintain the model's native smartness while also learning the new thing. So memory, by contrast, it's a much faster turnaround. It's more flexible. It's easier to sort of get right. It's more model agnostic. But there's a limit to what you can teach with memory. Like there's a limit to how much you can put in, and there's a limit to how much you can move the model away from what it wants to naturally do via this sort of contextually embedded memory. Which leads to maybe the last slide I have here of what are the open questions? One of them we already covered to some degree. How do you tail patch a model without forgetting what it already knows? Like let's say I just want to teach it 5 new facts, but I still want it to be good at poetry and good at instruction following, good at all these other things. And like this is especially hard when you don't have access to the data that taught it to be good at poetry and instruction following and all these other things. As soon as you start hill climbing in a particular direction, you move the weights in such a way that everything else starts to jiggle. And random jiggling in the other parts of the weights means, on average, it's probably going to degrade. On the other side, we have prompting. I think AI as a field is, well, I should say like LLMs as a field is kind of in its infancy of figuring out how to do prompting without just black magic. Like there's some people that are like really good at it and like they don't know why and I don't know why, and that's a little bit disconcerting. And this shouldn't be the case. Like I'm old enough that I was around when like feature engineering was still a thing in statistical models, and it had some of this aspect. But eventually we started to learn like, okay, these are the features that are consistently good and consistently bad. Step 1, always put in bigrams, and like you'll get a decent classifier. And we started to learn like the discipline, the loop of like try new features, train the model, see what went well, see what went poorly. Which I think is just starting to evolve in the LLM world. So as project ideas for bright young researchers, I think this is an area that's currently fairly underdeveloped. Related to that, like why does a prompt work on some models and not others? What parts of it are specific to the model and the eccentricities of a particular model? What parts of it are just generally good instruction following? Similarly, I'm not aware of particularly much research tackling this sort of thing. And how do you convince a model to introspect not its own uncertainty? We kept talking about critiques and error propagation. And all of this stems from the fact that these models are natively terrible at knowing when they're not sure about something. They're very happy to BS you about whatever you ask them to. They're very happy to reinforce whatever they think you want to hear, which is not actually conducive to building real systems. And with that, I'll hand it back to Spiros to conclude.
Yeah, I mean, just like final, maybe a couple of things that what's limiting agents now beyond like the things that Gabor mentioned. Actually, one metric I use when I talk to people who work with LLMs is, or one question asked is, do you hate LLMs? If you work with them long enough, the answer is probably yes. Despite all the amazing things. I think obviously like some of these were mentioned already, right? I don't have to repeat, but obviously like the reasoning abilities especially after let's say a long chain of calls and instructions, the context size window, the long horizon tasks. Another actually interesting limitation that we see is that a lot of the tools that are available we're giving to LLMs were designed for humans. And as a result, those are terrible tools for LLMs almost, right? So oftentimes they have no APIs. Now, maybe through computer use, you can get to like the human interface of these tools, but still, this is like a human pace tool in some sense, right? The throughput oftentimes is very limited. And we talk about these systems of record, I guess, in software especially, which are actually pretty bad for when you want to work, let's say, a lot more quickly, right? Or when you test hypotheses in parallel at a pace that humans cannot do, but LLMs can obviously do very well. And even humans themselves, ourselves, let's say, are kind of a bottleneck sometimes for these tools. An agent that is on call can be on call 24/7, never complains, will look at every alert you ask the agent to look. But then if a human has to also confirm something, let's say in that loop, oftentimes the humans ourselves become the bottleneck, let's say. And now there was this question that was asked earlier, which is, okay, what are the limitations of the context windows, right? How can we have an agent that runs constantly working on a problem? And I think in some sense, my view is that we're going to be moving in that direction, for a while. And a lot of the problems today, let's say, that maybe involve humans confirming might flip, or let's say maybe some of the problems will become easier and like the agents are going to be solving on their own, and then we're going to move to the new frontier of problems that we're not even touching today with agents, right? And require human intuition and human reasoning, let's say. But I think it's a constant push towards that direction, right? And for those of us who build agents, it's a constant push towards new problems, because like the problems we're solving today might become too easy and everybody's going to be solving them with LLMs tomorrow. And I guess that's what's coming. I mean, agreement with what Gabor said. It's very hard to make predictions, but I do think that models will keep improving and enable like longer horizon tasks that are very hard and break down today, and the reasoning fails. I think us as humans will move to a higher level of abstraction in general and keep managing agents. I do think, especially in software engineering, it has changed. We're not fully there yet, but I think that's the direction we're headed. So in some sense, systems thinking, understanding architecture, understanding, let's say, fundamentals even, is probably more important than like tools and code, etc. Human tools will be replaced, I think, by agent tools. And I honestly think this is a very interesting problem, or even for somebody who wants to build something, it's very interesting to like rethink, if we were to rebuild these tools that we build for humans, how would they look if we build them for agents? And it will move from goal setting to alignment and good taste almost, right? And I think humans will play that role, right? The role of setting the goal, setting the bar, deciding if the output is what we need or not, and asking the agents to do more work. And with that, thanks for inviting us, Jahangir, and thanks everybody for attending. If you have more questions, I don't know. Please. Okay, let's.
You've been spending lots of time on, say, like OpenTelemetry, and recently with, say, things like agents and LLMs, there's also been, lots of additions and expansion of the OpenTelemetry protocol. But then, do you think that this is kind of like adding too much overhead into the OpenTelemetry protocol, or do you see that there should be another, say, like telemetry protocol for these agents?
Okay, the question is, like using OpenTelemetry as an example, which is a protocol for telemetry based, right? Like, is this protocol, let's say, designed well in the world of agents, right? Because obviously we designed it for humans and systems of this nature. I mean, I think I don't have like a very good answer to give necessarily, but I do think that the way these protocols were designed were to describe states of the system, outputs, etc. Right? So there is nothing that should prevent us to use them in the world of agents, right? And in fact, the most useful type of telemetry for agents is tracing, because you want to see exactly what the agent did, right, and the states it moved through and the tools calls it made. And I don't see any limitations on how the tracing structure of OpenTelemetry in particular works to be able to capture the data you need for how an agent executed. But I don't know if you guys have another.
I think that one's squarely in your wheelhouse.
My question is regarding the guardrails. So you have so many agents running over there, and they have your customer and API keys. How do you know they're doing a good job? Do you reward them or punish them to be, accidentally delete the production database?
Yeah, the question is, how do you, you have an agents that have access to your production system, right, and have API keys to sensitive tools, how do you prevent them, how do you have guardrails for preventing them from doing things that are, you punish them when they steal your password and do something bad. I think in practice what happens, I'll tell you where the world is right now, right? This is a bit like self-driving cars, in my opinion, right, where essentially to the trust a human gives to an agentic system of this nature, is below its capabilities almost, right? Like, essentially we have to prove beyond doubt that this is not going to do something stupid, and then you allow it to do work. Now, from a design perspective, how do you add guardrails? I mean, oftentimes the guardrails come outside of the system in the sense that the tools, like Bharat was describing, the tools you give to the agent maybe have read-only access, right? Maybe at least, you cannot cause a catastrophic failure. Now, as these guardrails move into the agent itself, obviously trying to train the agents to not take actions that are irreversible or to high risk, etc. But that's not also easy, right? Because you're dealing with systems that follow instructions not very reliably sometimes. So for now, what we do, at least, a lot of the guardrails sit outside of the agent itself and more into the tools that it can call.
Here's my question. So we just witnessed how English became like the new code, right? But I was thinking, what's next? Like, once English becomes its own limitation and bottleneck, then what happens?
Yeah, sorry. So the question is, what happens when today English is becoming like the new programming languages? What happens when English itself has some limitations? And we already see that with programming, right? English doesn't always transfer unambiguously to programs. And I would say, even take a step further, English is already a bottleneck. For example, I don't code in English either. I code using voice because English is just too slow to type. So voice is maybe the next programming language, but that is also like English in some sense. So, but to better answer your question, there will come a point in software engineering, obviously, like how we do it today, at least like, for example, the guardrails and things like that, we specify them in English, and maybe that's not the best way to do those because English is inherently ambiguous. Maybe we should do it in terms of programs or some other language. I mean, there's not a definite answer to that, but yeah, that is definitely something that with time we'll see evolving. And I don't know if you've seen those videos of like two agents. I think that was mocked, but at some point that can be the true thing, where like two agents talk to each other and they're talking to each other in English and they suddenly switch to a different language, which is like beep bop, beep bop, beep bop, and then we don't even know what's happening. So that is a real possibility.
Though English is really good, we've built a lot using English, talking as humans with each other. And in some ways, I think actually the ambiguity is an advantage rather than a disadvantage. Voice, I agree. Like, certainly that's the future.
Do you have any tools or microservices that you found work better in this age where some tools translate better to these agents than others because they're more human-centric? And then the same question, like Superbase, that's great for database. And then the same question for like design principles, you kind of don't use monolithic structure so you can have differentiation with your sub-agents.
So the question was, what sorts of APIs are good for tool calling agents? And I missed the second part. Monoliths.
Design principles, like
How do you architect a multi-agent system, basically, when it comes to software itself?
I see.
Or how to architect the software so that it
Yeah.
lines up.
See. I think my general principle is do as few weird things as possible. So these LLMs
that
are...
sounds like life advice.
I know, just good life advice in general. Be as like, I guess this goes against what we're all taught as kids of like express your inner self, be weird, like don't be weird. The core here is like these LLMs still are fundamentally, completion models on some giant corpus of stuff that they've seen. The tools that are easiest to use are the ones that are least surprising, that look most like the bulk of stuff in GitHub that it's already seen. Have the fewest like weird API parameters and weird design patterns, which I guess is a bit of a cop-out answer, but it's maybe the best that I have. I don't know.
And one software design principle that you've learned and is good in this domain as well is like write good documentation. Even if you don't need it, the LLM needs it.
Yes.
And do you do your own documentation, or do you have the agent do the documentation?
I'll cop out. I mean, it's a mix of both.
He never writes the recommendation. Don't believe him.
At the beginning, you mentioned that maintaining production systems is exponentially more difficult. What is it exponentially more difficult at?
What was about, I guess the question is like I used the phrase maintaining production systems is exponentially more difficult than, I guess, when you're dealing with just one tool, right? One problem in software, right? When you're dealing just with code or just with logs, let's say, right? Because the combination of all these tools is, or the possibilities across them, it gets to infinity. But it's not so much about the tools themselves, but it's the data, right? So let's say if you're dealing with, let's say, logs or time series data, they just keep increasing, right? So you don't even know where to start when you're looking at the problem, right? Humans have a lot of intuition, of course, to limit, let's say, the area of exploration. But in theory, like a tool that is an LLM-based tool, where does it even start and where does it even stop, right? When it starts looking at, an infinite amount of logs that are being printed out from these systems. That's what I meant.
So is it fair to say that the complexity is coming from the interaction of all these tools?
Yes, and the interaction, and there is no, it's almost impossible to verify a result, right? You don't even know if you have the right result, ever, almost, right? So when do you even stop? Because it's not like a math equation that maybe has a right or wrong answer, right? Like it's a problem that, okay, something is slow, can you tell me what's happening? Like there's no clear, most of the time, it's very hard to know if you have even the right answer. And when to stop looking and